Good day. I believe it's been a nice time with you all there. Welcome back to the final video now for our class introduction to R for biological data analysis. We've talked about how we can read in our data in time past, how we can import them, how we can save them with a particular with our choice the variable name. We've talked about how we plot various charts in R. We talk about the bar plot, bus plot, we talk about the pie chart, we talk about the histogram, and some other of them. We've seen the scattered diagram and all the rest. So now we want to look at some statistical analysis before we call it a class. Let me use that word. So ANOVA, analysis of variance. Now most of us in the life sciences, let's say when we are performing our experiments, we have some experiment we want to perform that we want to test the effect of maybe 3 different doses on a particular animal. So we take the same, we administer maybe 0.5 milligram, 1.5 milligram, 3.5 milligram. Now this, each of them will be in various group A, group B, group C. Now how do you determine whether what you've administered, whether the dose has a part that it is playing in your outcome variable? For example, now in what you are determining, how do you know that? How do you compare? How do you analyze that? That's when we talk about analysis of variance. We talk about one way analysis of variance, 2 analysis of variance. I won't be teaching us statistics, but I understand. Before now we understand statistics. We have an idea of statistics. I'm just here to show us how we can perform some of all these statistical analysis in R, using R, that will make life little bit easier for us, especially when it comes to reporting. Okay, now let's go back to our tooth data. Let's go back to our tooth data. Remember, we've talked about how the tooth data came about. That has been talked about before. Now for us to perform statistical ANOVA, the function we need is called AOV. That is the function that performs ANOVA in R. Now we want to save, let's say, tooth ANOVA. We don't want to echo our results straight. We want to save it first, then later we can output. You see, AOV. How is length dependent on the various group? And the group want to look at the dose. We have 3 dose group. How is length dependent on dose? Does dose has any part is performing in the length of odontoblast? Okay, with that we enter. You are not seeing anything. Why? Because we have stored our results in tooth ANOVA. Let's just output tooth ANOVA right away. So you see it. Then before we look at the summary, output tooth ANOVA. You can see what it's giving you. It's giving you the formula you use. That the formula you use is length of odontoblast dependent on dose. How is that? Then your data is the tooth data. It's not giving you the sum of squares. You see it there, the residuals, degree of freedom, now giving you the standard error, and all the way. Now for us to have the summary of our result, say summary, then your tooth ANOVA, you can see it's not telling us that yes, the dose, the degree of freedom of the dose is 2, the residual is that, the sum of square is this, mean square is this, the f value, because in when you're talking about ANOVA, you have f value. It's now giving you the p value, which will tell you, according to the statistics now, whether the difference in the means is statistically significant or not. But as you can see here, this is extremely very low compared to 0.05 reference value. So it means there is a significant difference across the means of the three doses. Looking at the length, this is look at, it's even at what, at 0, that is significant at 0, not even at 0.5. That is these three asterisks you are seeing here, that it is significant at 0. That's what we are telling us here. If it was to be at 0.001, it will give us 2 asterisks. It was 0.1 to give us 1 asterisk. If it was to be 0.05, which is the standard or normal one, it will be dots there. Then we have 1 and all the rest. So that is how we carry out our ANOVA. Now, yes, we've seen that there is a significant difference across the three doses now. But where is this difference coming from? Where is it coming from? We don't know. To decide that, we use Tukey HSD. When I say our tooth ANOVA, we want to see, yes, where is this difference coming from? Enter. Look at it, it's not telling us, okay, between the concentration 1 and 0.5, the lower value, the upper value, the difference, the p value, that's the major we're interested in, it's 0.00. So there's significant difference here. Between 2 and 0.5 also, look at the p value. Even between 2 and 1, look at the significant value. You can see it there. That is what is showing us. So I believe we can now see how we can use R for our data analysis in massively for now to perform ANOVA. Now let's assume now we want to check, we want to combine the two of them. Is there a synergistic effects of both those and the delivery method? Because of what I did, we talk about synergy, additive effect and synergistic effect. Now, is there any interaction between the dose and the method of delivery when it comes to the length of odonto blast? Now, for us to do that, we use two different things. Let's save the first results. Let's say result 1. We want to check AOV of length dependent on what? On dose plus sub. The data we are using is tooth. Okay, let's save that. Now let's say result 2. AOV length dependent on dose times sub data equals tooth. Remember, the first one we use plus. Now we are using times. We are saving the results in results 2. Now we can echo each of them. We can output each of them. Result 1 for us to just see, so you can see what has been stored in result 1. You can see it there. You can echo result 2 to look at it. You can see what you have Yeah, you can use a summary to look at results 1. You can see there, and the result 1, look at it now. Look at in the dose. You can see that there's a significance, a statistically significant difference looking at this p value. Look at also for the delivery method when we look at the addition now. So definitely there's a form of interaction. Let's see. So at 0, it is statistically significant. But let's see the summary of results 2. You can see here, we see in terms of the dose, you can see this significance here using this p-value, looking at this p-value for the delivery method. Also you can see, look at this p-value. Now look at for the interaction between them. Yes, there's interaction between them. The interaction is significant at 0.02. Since them at 0.02, you can see it there. It is less than 0.05, and that is how we check. Now let's now use ANOVA on the 2 results to check the 2 results, to compare the 2 results. We say ANOVA. Remember the previous checking just ANOVA on its own, use AOV, then what you are doing. Then ANOVA result 1, result 2. Check what is giving you now. That's the model 1. You are talking about line dependent on those plus sub. Here, line dependent on those times sub. It's giving you all this stuff here. Now, if you observe here, you will see that the result here and here is the same thing. So there's interaction between the dose and the delivery method, and is statistically significant at what? 0.05. Okay, so let's see. Applied that. Then if you want to use Tukey HSD, also use Tukey HSD on that, just like we did before. Now let's talk about t.test, student t.test. Now there are different type of student t.test. You could have a paired t.test, and you could have an unpaired t.test. Let's look at we'll look at both of them. Now I want to run a what do I call it now? Just get some random figures. Got some random figures. Look at here. I'm saying give me random number, 30 random numbers. I want the mean to be 3. I want standard deviation to be 1. And here also I say give me 30 random number. I want the mean to be 3, and I want standard deviation to. So you can see the two of them. Logically they are the same thing, but mathematically they are not the same thing, because it's a random number. So picking 30 random numbers, let me say Mr. A picking 30 random numbers and Mr. B picking 30 random numbers, and both of them picking the same thing. No, the chances is almost infinitesimal. So let us put it. Let's see pre B. You can see, okay, let me round it. Let me say round pre B 2. Okay, so you can see that what we're having in pre B. Let me say around pre post B 2. You can see what I have here now, 7 clues that there is a difference between pre-B and post-B. Okay, let's ask R again now. Sorry, I'm not able to go online now. However, the same thing you have like we've done before. You read in your data. Let's say your data is house tax, for example. You save your data like that way. You can view it. To run chi-square, all you need is just chi-square dot test, then your table, your contingency table. Now the contingency table, which contains all which contains your the data sets you want to check, you want to look at the chi-square for, and with that you have your chi-square. Once you do it, you declare your chi-square and you can get the results of your chi-square. Okay, mosaic plots, not do that. That's another thing entirely. Is into the ggplots too. Okay, now let's do regression analysis. Now I want to read in the data set iris. Now here look at some flowers, 3 of them, 3 flowering plants. Look at their sepal length, their sepal width, their petal length, and their petal width. Let's see, I've loaded in my iris. Let's see summary iris for us to see what's. Now you can see here that we have sepal length, shows the minimum, the maximum, other thing. We have sepal width, petal length, petal width. Then we have the species, each of them. 50 of this flowering plant, 50 of this flowering plant, 50 of this flowering plants. Now we want to look at, is there a relationship between the sepal length and the petal length? Is there a relationship? How do we go about that? We use LM, linear model. There are various type of regression analysis. So LM, let me just show you, sepal dot length dependent on petal dot length. What data are we using? Our data is iris. Okay, let's have it. You can see it's telling us, giving us the intercepts. Remember, a straight line graph. We have a straight line graph that was giving you this, on your y-axis or your x-axis. You can have your intercepts there on the y-axis. Then talk about the slope. So here, this is our slope for this relationship. This is our slope, and this is our what now? This is our slope. Our slope is 0.4089, while the intercept is 4.3066. Let's plot that of let's look at what the relationship between the weights and height of women that we look at initially. Let's say weight dependent on height. Data equals women is giving us the intercept to be minus 87.52 and the height to be 3.45. So from this, remember our equation of a straight line graph. I'm going mathematical a bit. Plus C, where M is the slope and C is the intercept. That is what that is giving us. So let's assume that we don't know the weight of somebody, but we have the height. And now we know that 3 87.5 times height minus 87.52 will give us the weight. So how would we get that? Let's see now. Let's say slope. So the formula for that height is just that 3.45 times what? Times the height plus what? Minus the intercept now. 87. Let's say minus 87 intercepts. So that some of us can understand what I'm saying. Okay, so let me explain it now. I know the height to be, let me say the height is 35. Okay, 35 minus 87 point 87.52 was the result. It's giving me 33.23. So for somebody whose height is 35, then the weight that is based on that data set that we have up there. Okay, let's run this. Let's assume we save our separate length dependent on this this equation. I want to look at the summary. That's another way. The summary, my equation. You can see all the various things is giving you, putting it out for you. So you can go around that depending on what you need. Is there a statistical difference between them? Yes, that's what it's telling you. Look at the intercepts there. Look at you have the slope also. So that is linear model there. If we want to draw the plots, that would be if that will be using ggplot2. So I will see what I can do here now. Now here I did something. I say plots. Some of all this may not look relevant to us, but just for you to have idea of it, I say plot my equation. That is what I've stored in my equation there. Plot it. You know, it's not telling me okay, hit return to see the next plot. You'll be showing me different plot now. Look at a scattered plot. Look at another one. Normal. This one makes sense for the people in statistics, but do not make too much sense to you. You understand? And we have it that's way. Okay. So now let's have a peep into ggplot2 when it comes to this linear model, for you to see that what you will not do effectively with base R in terms of linear model, we do it effectively with ggplot2. Let's say I have my ggplot2. I have my ggplot2 loaded. Okay, and I said okay, give me plot of women, give me separate length, beta length. Now use color to separate the species for me. Object separ dot length not found. Okay. Oh, I look at it. I was using women instead of iris. I was using women instead of iris. So it's looking for another data set. Okay, you can see it brought up for me the petal length versus. Now, I've not given it the type of graph I want to plot, but it has already given me the pin. Okay, what there's another information you need to give me for me to plot this for you. And I said, okay, I will now add this geom points. You will see something. You can see, look at 3 different points. Look at, this is one of the flower, this another one here using green, this another one in terms of blue. And look at here, I've been given the legend to distinguish them. Okay, let me go forward. Let me say, okay, I've seen that. I want you to add the linear model now. You can see that added it to me, that added that line to me there, that added the line of the relationship between them. Okay, let me now say, remove this shade. Remove that shade. That shade is giving me the standard error of mean. Okay, let me say there that standard error of mean equals false. I don't want you to put it. You see, the shade has disappeared. The shade has disappeared. Okay, let me now inform it now. Okay, I now need a linear model added to this. Say start smooth. The linear model, I want the method is LM as a linear model. You can see it has given me this stuff. Okay, I need to remove the SC equals false. You can see it added that line there for me, and with this I have my graph for each of the flowering plant, the relationship between petal length and sepal length. I've shown you how we can get the equation that we need so that we can extrapolate anything we need. That is what you can use. Let's say, for example, you are plotting concentration against absorbance, so that okay, you now have absorbance. You want to extrapolate the concentration from that graph or that equation of your line straight line graph. You can extrapolate your concentration. That is how you apply that. Now let's see correlation analysis. We have these data sets of the women already. Now for our correlation analysis, when you use core like this, it gives you the correlation coefficients. Remember, correlation coefficient R is between -1 and +1. If it is -1, it says there's a strong negative relationship between the two of them. But if it is +1, it is strong positive relationship between the two of them. The straight line graph will tick to the right. If it is negative, it will tick to the left. Then between 7.5 to that one is strong. But if it is between like 5 to 0.74, we can say it's moderate. and all the rest, or when there is no any correlation between them at all. But if we want to check the test, between the two of them, the association, the correlation between them, we can use core test, the function core test. Now let's use core to check the correlation coefficient between women weight and women heights, and women heights. It's giving us, if I can see, it's a very strong correlation between them. In fact, it's 1, because when you approximate 0.995, you approximate at all, you have 1. So it's a strong positive correlation between weights and heights for the data set we have. Now let's check the test. Now let's see some of the parameters that will be you get as outputs. Rather than typing, let me just say core.tests. Okay, you can see it's giving me various data here. Now you can see it's the pearson. We have different types of correlation analysis. You have pearson, you have spearman, you have kendall. Depending on the kind of data set you're using, that will inform the type of correlation coefficient that you will need. You now have to specify the method, whether it is pearson, it is kendall, or it is spearman you are going to use. So you can see the data set here. Now we're talking about relationship between women height and women's weight. It gives us the t.test, give us the degree of freedom, the p-value. You can see that there is a significant difference between them. So there's a strong association between them. That's what this one is showing us. But the two of them, they are statistically different. Definitely the two of them, they are different. The height is significantly different from the weight. Okay, if we were to use if as me we were to specify another method of correlation association, now we just do the same thing, but this time around we just say method. We specify the method, spearman. You can see it's giving us another sets of stuff, what we need there. And if it is kendall, you just the method equals to kendall, and that is the correlation analysis that we are having there. I hope so far so good. We've gotten that. Let me see. We've done that. Yes, we've done all that. Okay. Now let me do what we call correlation matrix relationship. Want to see what we call a correlation matrix. Let's see it. To do the correlation matrix, you declare. Now let's see our iris, for example, so that you understand what we are doing. This is our iris. Now you can see from our iris, there's what we need is a numerical data. You can see from our iris, I intentionally declare it so that you can understand. Normally I'm not supposed to do this. Once I just use summary, I get what I want to get, or names, I get what I want to get. Now you can see here, this is numerical data, numerical. but here it's not a numerical data, so we don't need this for correlation matrix. We don't need this this last column for correlation matrix, because they cannot get anything out of it. It's only these ones that are numerical that you can do matrix on. So we now want to specify that, okay, from this iris we want to select column 1, 2, 3 and 4. We want to select column 1, 2, 3 and 4 and all the rows. That is what we did there. That's what we did here. We said, so iris core, give me, let me take it one by one so that you can get it. So I said iris, subset it. To subset it, you use the this breeze type of what do you call it now, bracket. Now you can see in the first one there is nothing there. That is meant for the rows. Now I now put a comma, then I came here. This is meant for the column, and I said from column 1 to column 4 you should give it to me. That is what I have done there. I hope we get that. Okay, so I now save that as iris. I said iris core is what for correlation matrix you use core. Give me column 1 to 4. Perform a correlation matrix on it. Now, because I've saved it inside iris core, that's why it's not displaying it right away. Let me display it right away for you to see what I've displayed. You've seen it here now. Now, let me say, give it to me in 2 decimal places, round, so that you can get it. Round, iris core 2. So you can see it better now. So here, relationship between sepal length and sepal length. Here, relationship between sepal length and sepal width. Relationship between sepal length and petal length. Relationship between sepal length and petal width. The same thing here. That's the matrix that you have seen there. Now, with core plots, we can change this into a diagram, graphics. Say core plots iris core. I want to visualize it now. We have gotten the data itself, the relationship between them, the coefficients, that is correlation coefficients. That's what you have gotten using that core. So we want to now visualize it. Okay, I didn't load my library. Okay, so core plot iris, look at it here. You can see it's showing us relationship between them, and it's giving us the interpretation. You can see, so this is strong. Definitely you expect is 1 sepal length versus sepal length. They are the same thing, so no story. This one also no story. You can see, and if you come here, you can see 1. You can see 1, 1. You can see 1. You can see 1. So what we have done here, we have just visualized what we're doing here. So you can see here that there is a strong correlation between sepal length and petal length, and there is strong correlation between sepal length and petal width. You can see it here also, 0.87. There's a way we do it, that here we will indicate the value of this. It will show this and also indicate the value. But all these are part of the things that will come up in under visualization under the second module. So I believe we've gotten something interesting from there. Let me just do heat map. So there's nothing much in our listing for that. Okay, so this is where we'll be ending the class. I believe it's been a nice time. Thank you very much for making yourself available for this training. I hope to see more of us. If there is anything you want to do that you cannot, you can contact me. And if there is many reason for collaboration, you have data and you need any form of collaboration, we can work together. As far as it's within the life sciences, since I'm a biochemist, and it's been a nice time with us. So I really wish us the very best. Thank you very much. Bye.